Be strong.
Answer. Right. So electron transports, I just mentioned how they change the dipole, right? You have molecules. In this case, the molecule is charged, positive charge, right? Your surface has more electron accumulation. This reverse the effect of dipole we introduced, right? By making the electrons escape easy, right? It's sort of the reverse dipole on the surface. You think about it, that repel the electrons and also the top positive charge sort of have to this, pull electron out of from the surface, right? Any questions? Okay, then we continue. Talk about these carriers. We just stop here, right? That is, we can use different kind of thermal to excite the electrons, right? To create free carriers. Right? We can dope the materials with p-type, n-type dopant, right? So for that, we can create pin junctions. The pin junction is a very important building block in semiconductor electronic device. You can make the diodes, you can make the transistors, right? A solar cell, LEDs, all these. Very important to create pin junctions. What is pin junctions? So you use silicon as examples. You have NP doped cases, right? For N-type, you have created a lot of free electrons. You have if you create then you have this donor dopant, right? You have on the right, you have boron, So a lot of electrons, when you make them in contact, these electrons will drift, a lot of high concentration and flow to the low concentration, and these holes also flow towards these contact regions. Then the electron hole will recombine. Right? They quench these free carriers, right? So that's the create additional so-called depletion rooms or space charge rooms. So because when you pinch the electron holes, these mobile, you will end up with the static non-mobile ions left behind, right? So those are the, you create a region without the free carriers. So these space charge regions or depletion regions. So then this can also in the same time create an electric field that prevents the further electron holes to recombine. So I think this picture illustrates better about how this is going on. So this is illustrate the carrier concentration, electron concentration in the undoped region that gradually decrease and eventually becomes zero towards p-type, right? The holes, the carrier concentration decrease across these space charge regimes and decrease to zero. This is before you apply external electric field, right? So this is the space region. In the p-type region, you have this static negative charge because the holes combine with the electrons, right? Left behind. This is positive charge left behind. So this is neutral regions. And you see that you created the electric field. Then this electric field just exerts the opposite force for the electrons, right? To continue to move this towards on the left because of the repulsion of this negative charge, right? The same for the holes. The holes will repelled, they remain on the left. So there are no more free carrier across these space regions. Then the situation changes when you apply external electric field, right? This is the zero bias case, right? You have this energy diagram when you align these contact P and N-type. This is the Fermi level. As long as you make two material contact, the Fermi level will be aligned. This is the equilibrium. So then you have this conducting band, valence band, right? So in this case, this is N-type regime, right? The Fermi energy is close to the conduction band. This is the p doped region, right? This is p. You have a lot of positive charge holes, electrons, right? So that creates a space charge regions and building electric field in this space charge depletion regions, right? Then you can apply the voltage across these p-n junctions. One is considered reverse, another is forward bias. Reverse bias means that there is no current flow. Forward bias, that the polarity of the bias applied just right, you can turn on the current flow. So, and how that going to happen? The reverse bias is that, you see, this is your battery. This is your battery. You can think about it. You connect a battery to the p-n junctions. If your negative end is connected to the p-doped regions, there is no current flow because you are going to, if this side is negative bias, these energy levels will push up. The electrons, if you want to cross this on the right side, it sees a much higher barrier, right? You cannot cross. But if you reverse the polarity of bias, you make this right side positive charge. Positive bias, you move everything downwards. Then the electrons will be heavy, you see much shallow barrier. So at a certain point, you just drive across by this external field. You can cross conduct current. The holes move to the right. You can turn on this. So this reverse bias, no current. Forward bias, you have to keep reducing till the barrier is small enough for the electrons to cross. You have the threshold voltage that basically the minimum voltage that must be applied across p-n junction to overcome the intrinsic building electric field. So you can turn on the current. So this is a so-called diode behavior when you have p-n junction, right? Depending on your voltage and polarity, you can create only certain electron can only flow when the bias is right. So this p-n junction is the basic building block for these transistors, solar cells, right? So you can see that this is a very typical representative field effect transistors. You have these p-n junctions, right? You have n-type doped silicon, then the main body is p-type silicon. So you have this interface, right? These are the p-doped. You see, if this is your metal contact line, in order to drive the electron flow across these regions, you have to flow from N to P, P to N, right? You have to deal with these p-n junctions, right? So one typical type of field effect transistor called this, MOS field, it's basically metal oxide semiconductor field effect transistor. Here, in addition to this source and drain, you have the gate. The gate electrode, basically you have the metal. At the bottom you have gate oxide. The channel is p-type silicon. So you apply this voltage between the gate and your p-type silicon. So your p-type silicon, you can think about it as a conductor. Basically, you have an insulating layer between. You have two metal plates. You have the voltage across, right? Basically, the capacitors. You can charge. You can charge these two materials, right? But the introduced gate oxide is basically prevent electron tunneling when electron flow between the gate and the p-type silicon. But the way how this architecture is that you can create the free carrier inside the channel. Once that create, they can allow the electron flow from N-type to the channel and to the right side, so that you turn on this device. And the switch here is use the electric field. So that's why we call it field effect transistors. But how to turn on this device? So without electric field, this kind of configurations, right? Without gate, we do not expect the current flow, right? Because the current electrons cannot cross from N to P, P to N. There's built-in electric field, right, to prevent them to flow. So you can think about this when you apply the right gate voltage. This top gate outside the channel, you basically turn it 90 degrees. This is how that you can view that. This is a gate sitting outside. You have P-type channel materials, right? So this is before you apply gate, connection band, Fermi level, valence band, how they aligned. When you apply negative voltage, what does they happen? The negative gate voltage, that you negative bias your metal, so you accumulate a lot of electrons, negative charge, right, on this conducting plate. Then opposite, you will attract positive charge, double capacitor model, right? There are a lot of positive carrier accumulate near the silicon dioxide. So that also cause the band up when you apply this negative gate voltage. That basically repel the negative potential, repel everything up, and from another the host try to move to these states with more close to the vacuum level or Fermi level. So in this case, there is no current flow between the source and drain. Okay? The electron cannot cross this barrier. You basically enlarge the barrier for electron cross from N to P. But if you apply the pot gate, the things will change. If the pot gate is not large enough, there are also no current. What happens when you apply pot gate, you accumulate pot charge, right? Then you sort of try to also repel the particular host away from the interface, from silicon dioxide. You create a depletion regions. There are no current flow, and the pot gates basically bend all the states downwards, right? So this bending is not sufficient strong. But if you can increase the pot gate, and the conduction band or valence band, they bend till they have the so-called inversion. This conduction band tail already cross the Fermi level. What does that mean? Cross mean the empty states cross Fermi level mean being occupied by electrons, right? So in the real space, you will see that there are accumulation of the electron carrier right at this silicon dioxide inside the P-type P-doped channel materials, right? P silicon. So on the left, the source and drain, it have this a lot of electrons, right? Electrons. When you have this inversion layer, you also create electrons accumulation inside this channel from the P-type of materials by gating. You see, the electrons, you sort of open that channel, that can open the current flow. You have on states, you create a source drain current. Okay, you turn on the device, right? Using the gate. So here is the source and drain. Source is the charge carrier, the electrons from N channels, host from the P channels. The drain is the valence charge carrier, electrons here leave the channel. Right? So the source drain carrier current basically depends on the channel width. The channel width carry more current, right? And also the channel length, the large length have high resistance, right? Reduce the current, and also the thickness of oxide. That change the capacitance effect, change how much carrier you can accumulate in the p-type junction at certain bias, certain gate voltage. Okay, And also this current depends on the mobility of the carrier move across this p-type silicon, right? And the capacitance and also the proportion to the square of the gate voltage applied that define the current flow across these junctions. Okay? So this is one typical field effect transistors used in our computer chip, the chips using your handphones, right? Okay, that's the basic fundamental concept of semiconductor. That's I think we leave few questions 2 and 3 later during the break time. So next we talk about some typical coagulation technique used to understand advanced electronic materials. Okay, so there are different types of 2D material I mentioned earlier. Okay, there are inorganic materials, right? I mentioned. There are also these new type of inorganic and organic hybridized perovskite materials. I think in the first part of Professor Tan's lecture, they have talked about the perovskite. When you perovskite, you have the inorganic perovskite, organic and inorganic hybrid perovskite. Now you have purely organic perovskite-like materials. All these different type of materials, when you characterize at different landscape, using spectroscopy, using imaging, you have to understand the structure of the materials, the fundamental principles of the tools you can use to understand the properties. So very often, XPS is widely used to measure the materials, right? So XPS we call X-ray photo emission spectroscopy. So that's what is the working principles? Here I'll just briefly go through that. So X-ray, basically the source. When you try to understand the materials, you need to have the probing kind of particles. You can use the electrons as a probing source, right? You use the photons as a probing source. Let them interact with your materials, right? After interactions, they will carry some information. Then you analyze the particles from the escape from your materials. Then that particles will tell you the information associated with your material. That's basically applied to all the coagulation techniques. For XPS, you use X-ray source. X-ray is the photons. The photons, you shine the photons to your materials. You get what it can get. You get the photons or get the electrons from your materials. In terms of XPS, when you shine the photon, you analyze the electrons escaped from your materials. That photons in, electrons out. When you use the electron microscopy or electron spectroscopy, that you can use electron as a particle source to probe their materials. Then you can generate the electrons, you can generate photons, depending on different type of coagulation, right? So here the XPS is photon in, electrons out. The photons can generate electrons. That you use the photon electron excitation, right? It's called photon electron, excitation, right? Effect. So the electrons inside materials gain energy from the interaction with photons and become energetic, can overcome the barrier of work function, the binding energy, right? It can become the so-called photoexcited electrons. Then you can enter into your analyzer, you analyze the energy of these outcoming electrons. This carry information. So in terms of XPS, very often we excite the co-level electrons. For example, this copper, a piece of copper, you can shine electrons, right? You can use XPS, right? Irradiate. Then you can excite the co-level electrons from 1s to s energy levels to excited, to escape. Then you analyze the kinetic energy and then divide by the energy of electrons. You can, from this position of this characteristic core-level excitations, we can understand it's metallic copper, it's oxidized copper, right? And copper bonding to oxygen, copper bonding to sulfur, all this, right? So basically the basic idea. But how to achieve that? So energy conservation here, right? You have the coming photon, X-ray photons carry certain energies. Typically, X-ray source used in a lab is based on energy K alpha emission. The energy of these X-ray photons is well defined. Okay, that basically determined by the energy difference between these atomic levels that involved to create X-ray source. So it's characteristic emission with particular energy. So if you use manganese aluminum source, you know these photon energies. Now photon energy excite core-level electron excitations, right? And the electron escape the barriers that become photoelectrons. Photoelectrons, once you escape, they carry the kinetic energy. Right? They have some kinetic energy. Then, if you do this energy conservation, the coming photon energy, it will be used to overcome this energy barrier from vacuum to this core level. So that equals to binding energy of this core level plus the work function. So then plus the remaining kinetic energy of your electrons. So they are equal, right? From this, okay, if you know the work function, if you know the photon energy, if you use the detector to understand, to know the kinetic energy of electrons, we can analyze, derive the binding energy of that core level, right? So the binding energy here is the energy difference between Fermi level and the core level. Is this. For 2p core level is this. Right? Then the kinetic energy here of photon excited electrons. The definition of kinetic energy is with respect to the vacuum level. So the difference between them, then you have to add the work function here, right? So the kinetic energy of photon electrons, you can divide this equation, that equals to photon energy minus binding energy minus work function, right? Any question? Okay, here I have one question. So in how to figure out the, here you see that to know the binding energy of your sample, right, you have to figure out the work function of your sample. So when you pass the sample to measure XPS, right, did you tell the operators the work function of my sample is a few eV? Do you need to provide this information? No need, right? They will automatically generate a spectrum for you, and you use certain software, you know the binding energy of this carbon mass, nitrogen mass, right? You didn't tell them the work function of your materials. And if you have to tell that, you have to scratch your head, how to figure out the work function of my sample. It varies a lot, right? But the good thing is that you don't know, in a real operation, you don't need to know the work function of samples. You only need to know the work function of your spectrometer, your XPS spectrometer analyzer. For that, we can calibrate the supplies, we know that the work function of spectrometer. So if you look at this, how the entire XPS process, you see that to generate the X-ray photons, you shoot the electrons, bombardment and metal. This metal can be magnesium, can be aluminum, right? You have the X-ray emission. Once you have this X-ray emission, right, this this X-ray, this X-ray shine to the samples. They will excite the electrons. into your detector, analyzer, right? So here it is, the X-ray first goes through this monochrome method that select, just get all the photon with the exact identical energies before variate samples. After that, you create your photon emission and enter into analyzer. Okay, from sample to analyzer. Then the work function of the analyzer here matters. Okay, instead of from energy diagram. Okay. Right? So your sample escape from sample, eventually these electrons will enter into your spectrometer. But during the measurement, your sample and the spectrometer are connected. So their Fermi energy are aligned. So that the photoexcited electrons first overcome this fine energy, overcome this work function of sample. And once into your spectrometer, it also has to overcome the difference of this work function difference between your spectrometer and sample. So you see that your kinetic energy has to minus this spectrometer minus the work function of the sample. So eventually, actually, the kinetic energy of your electrons will equals to photon energy minus binding energy minus the work function of the spectrometer. So this problem can be solved, right? So once you have the kinetic energy, you have the spectrometer work function, you can figure out the binding energy of the elements. No matter which sample you send to me, right? I don't need to know the work function of your sample. I just need to know the spectrometer. This can be a fixed value, right? Right? Okay. Then the exact binding energy of the electrons, co-level emissions from depends on the chemical environment. That's why XPS is very chemical sensitive. Right? For example, this carbon, we can measure the carbon, so different kind of element. If you plot the binding energy of this carbon that bond to different chemical species like fluorine, CO2, CH, the binding energy actually increase from left to right. This is because if you want to drag one electron from the carbon valence orbitals, because of the electron affinity, activity of fluorine or this, make the carbon more positive charged, to make it harder to escape. The harder to escape, that means that you increase the binding energy, right? So it means the electron lies in the deeper level. So the change in this chemical environment, all the oxidation states or elements, right? Local chemical physical environment change the binding energy. So this sort of provides a fingerprint to tell you the environment of your element inside your compound, inside the solid, right? So the high oxidation states, high binding energy. High oxidation states of carbon, that means the carbon itself is more positively charged, right? So the chemical shift depends on the overall charge of your atoms. All these the substitution groups, because also they change the charge states of your carbon, they change the binding energy. So the high oxidation states, high positive charge, that means you create a higher binding energy for the certain co-level emission. The same for sulfide, because it's Coulombic interactions, so increase the binding energy. So this is one of the examples. For example, if you use XPS to measure these different kind of organic molecules on the solids, on the 2D materials, right? This copper PC, fluorinated copper PC, you see that you have seen different kind of you monitor carbon valence co-level emission, right? For the bottom blue curve, you measure for the copper PC, the carbon, you have these 3 binding, 3 peaks. Okay, there. One is assigned to carbon that connect to the hydrogen. those carbon, right? Then another carbon connect to the nitrogen. For example, this kind of carbon. The different kind of carbon species. That is connect to the nitrogen ones, they show the higher binding energy. Nitrogen has a higher electron affinity, right? Make this carbon more positive charged. So increase the binding energy. Then, if you replace all the hydrogen with the fluorine atoms tend to grab the electrons. Right? So you see all these peaks shift to the high binding energy. Right? That's very sensitive. Now you have, instead of have two, you have three peaks. The carbon connect to the carbon, carbon connect to the nitrogen, carbon connect to the fluorine. This you see a much large peaks associated at a high binding energy that you have a lot of the carbon connect to fluorine. Right? So it can change by a few electron volts, which is very sensitive, right? So imagine that you have the graphene. If a chemist, in the early days, they try to process graphene. In order to process graphene, we have to oxidize graphene. We throw the graphite into this very harsh environment. We create a lot of oxygen on the surface. You can use XPS to make the samples. You see that you heavily oxidized graphene called graphene oxide. The layer of graphene has a lot of oxygen groups on the surface. You can see that you have the component from the assigned to sp2 component. Then the carbon link to the oxygen, carbon double bond. This gradually shift to the binding energy towards a higher energy, right? High binding energy. But if you use the vacuum heat or the chemical heat, chemical reduction, you remove certain amount of oxygen on the surface, actually creates, you collect the spectrum of this, you will find that, you see that sp2 component increase, while this carbon link to the oxygen component decrease dramatically. So this also can use to monitor the oxidation and reduction of the graphene oxide. Right? So in addition to XPS is using photons to excite the cold-level emissions. But there are also another technique called angle-resolved photoemission spectroscopy. This is also very powerful. Instead of excite the cold level, here excite the valence band level. Valence band. So you go back to this. You have this conduction band, valence band, below the Fermi level. Instead of excite these deep cold levels, you can excite the electrons, shallow electrons that lies at the valence band. This part is interesting for transport or determining other properties because you can excite electrons easily, right, without where you put a lot of high energy. So, angle resolved photoemission spectroscopy, so-called RPAS, is able to use low energy photons like UV to excite the valence electrons. And this, once the electron excited into an analyzer, in the XPS case, we mainly analyze the energy. But in the RPAS, instead of energy, we also analyze momentum. You know the electrons, particles carry the energy, carry momentum. The momentum is associated with the band structure, right? In the K space. So you have energy conservation, you have momentum conservation, the incoming the electrons, and before incident and after the final stage, they have to conserve. Right? So from the detector, you can analyze the momentums that for the 400 nanometer to 700 nanometer. And if you use this RD equation, you will 0.61 times wavelength times this numerical aperture, actually get like divide by 2, right? 200 nanometer. That's it. Use 400 nanometer, as source. So this R is the sort of minimum distance between two physical objects using optical method. So how to get these RD equations? How it come from, right? So we know that we can use this to estimate the optical limit, the resolution limit of the optical microscope. So this is boiled down to the light diffraction phenomena. For example, you use optical as a source to image. Right? For example, you have the point source. It can diffract light. When light has to reflect, light has to enter through the aperture, a small holes, right? When the light is a wave, right, escapes, penetrates through a holes, you have this diffraction. Even you have a point source. After that diffraction, it appears as an airy disk, much broad. The center is bright, but because of diffraction interference, it creates this maximum intensity at the center. In the meantime, you have oscillation gradually die down. For each point source, it creates individual areas disk. You have the 2 point source. They create 2 sets of airy disk pass through the holes. So if these 2 airy disks overlap together, you cannot differentiate these 2 objects, right? You have to barely differentiate. That definition is defined by R. So at this point, your maximum of your first airy disk overlaps with the minimum of the adjacent airy disk. So, and also if you know the theta and the size of these holes, you can do the mass calculation. Then you can derive this AB equation based on this criteria. That's the determination of the optical microscopy. So then the bottom is N and NA. NA is numerical aperture, which equals N times sine theta. The N is the reflective index. For example, in this optical, the lens, right? So you imagine your object at the bottom, this reflected light will pass through the vacuum or pass through the air. Then this N is the refractive index of your air. If you immerse your lens in the oil, instead of exposing this air, right, you are going to increase the N. We know that refractive index of oil, is bigger than the gas, the air. So if in that case, that you increase the denominator, the numerical aperture, right, that you can increase. You can make the R smaller. When this R smaller, that means you can improve the optical resolution, right? And you need to operate your optical under the oil, which is not so friendly, right? But that can improve a little bit. But it doesn't create a dramatic change, right? But second is lambda. You typically use visible light, right? But if you want to improve have better resolution, you have to reduce the lambda dramatically, right? You can use a 400 nanometer that, right? You still, stuck at 200 nanometer range. How to push this even forward? We can use X-ray for optical imaging. In principle, yes, right? X-ray is high energy, lower, smaller wavelengths, but it's not easy to operate with X-ray, right? Using optical. It's, you even use the gamma photons, which is not so friendly to us, right? So not good. Instead, use the photons. Then we can overcome this diffraction limit. That using the electrons. The electron is much nicer than the photons. The photons have the wave, can be considered the wave, right? The electrons also have the wave-particle duality, right? You also have electron waves. But electron also has a wavelength that depend on its energy, right? So the good thing is that the wavelength of electrons can be tuned by changing its kinetic energy. That's good. So the wave-particle duality of the electrons is defined by the de Broglie equation, right? The lambda of the electrons is equal to the P over, the H is Planck constant, p is the momentum of the particles, right? That is m times v. So then m times v is the momentum of the electrons, also associated with the energy of the electrons, right? So for the electrons, the good thing is that it carries the charge. Charge means that it can feel the electrical potential, right? Then you apply the external electric field, it can accelerate. But for photons, it's neutral, right? When you apply electric field, it cannot accelerate the photons, right? So the electron gain energy when you apply the potential, right? So it will get accelerated. So from this voltage applied, you can derive the momentum of your electrons, because the m times v velocity, you can get this substitute into this de Broglie equation, you get lambda, right? You increase the acceleration voltage, you are going to decrease the lambda. So if you increase the voltage, you are going to make the electrons travel much, much faster, right? And there is a limit. The limit is how fast the electron can travel, the maximum speed. Maximum speed, can it travel even faster than photons? Cannot. The light's travel speed is the limit, right? So you cannot. This is governed by the relativistic effect. You sort of, as the particle travel faster, that creates sort of effective mass. It's harder to accelerate even higher velocity. So you have to introduce these additional terms to characterize that due to this relativistic effect. So you see that this basically you increase the voltage, right? Those are all the positive terms. So that you further increase the value of denominator. You make the lambda even smaller because these correction terms. Kilovolts. You see the difference. The classical one, the one with that addition term with the relativistic effect, that take a major impact when you have the high acceleration voltage with around 200 kilovolts. Below 100 is almost the same, but above the 200 you start to derail. So, but if you look at the absolute value, the valence of electrons can be modified to the picometer. Picometer, what is the concept of picometer? 1 nanometer equals to how many picometer? How many picometer?
10 to the power of 3.
1 nanometer equals to how many picometer?
1,000.
1,000? How many? 1 nanometer is 10 to
Minus
9. 10 to power 9, right, meter. This picometer is 10 to my power 12. It's 1,000, correct? 1,000. 1 nanometer equals to 1,000 picometer. So just now the photon is emits 200 nanometer. Here's how many times? Like reduced by 10 to the power of 5 times. So the wavelength of electrons is very, very small as compared to photons, right? So when you use the electrons as the imaging source, there is, in principle, no diffraction limit anymore. If you from the wave point of view, right? The wavelength of the electron is so small, it's not a so in principle you should have much, much higher resolution when you use electrons as imaging source. But very often you cannot get such higher resolution. For example, you in the TM we use 1,000 or the 6,000. You see that your wavelength of electron is picometer. But if you think about the bonding distance inside the molecules, inside the silicon distance, carbon distance, what is the distance range? The carbon distance in the benzene molecules is what? How much? 1.42 angstrom, right? 1.4 angstrom equals to 142 picometer, right? So two atoms, they are separated by 142 picometer. Then your individual electrons wavelength is 2 picometer, which is much smaller than the two objects you are going to differentiate, right? In principle, the wavelength of the electrons is nothing inside the electron microscopy. But in reality, the electron microscopy, very often you cannot reach higher resolution. There are other issues you have to deal with. That is the lens to focus the electrons is not perfect. You have that lens limitations. But using electrons as a source, definitely much better, of much higher optical resolution, real space resolution. So in addition to that, the electrons also have other good things is that you can accelerate the electrons by voltage, apply voltage, so you can change the wavelength, right? And also you can focus the electron beam. You are not going to use a single electron. You shoot a lot of electrons. You have the electron beams. Then you need to confine these electrons. You need to focus the electrons. Then very often we can use the magnetic nets. We can apply a magnetic field with certain distributions. When electrons go through this magnetic field, undergo the spike motion, they can focus the electrons to make the spots very small. That can further enhance the resolution. Right? So that's the advantage of using electrons. So two common techniques they use in the basically just sampling here. You have the electron source, you focus, you shine radiate your sample, then the electron transmits through your sample, and you analyze the electron transmitted through your sample. This is transmission electron microscopy. But in the SEM, scanning electron microscopy, as in scanning, basically here you have the electron source, you focus, you have the electron beam, and then you apply this magnetic field to bend this electron beam. This electron beam just scan all your samples. Then you have the generate the second electrons. You regenerate electrons enter your detector, and these regenerate electrons carry the surface morphology information. So this can use to analyze the morphology of samples. So in terms of advantage, the TEM usually offer a much higher spatial resolutions. You can visualize the lattice. You can even see the atomic position in certain modes of the TEM, like scanning, transmission, electron microscopy. The resolution is much higher than SEM. But SEM has certain advantage. You can measure the sample with a higher vertical resolution. That means your sample has up and down the roughness, right? You can measure 6 samples because it doesn't require the electron to pass through samples. But as you scan the electron on the surface, you can see this congregation. So this has a large depth of field. So they are sort of complementary. So why the TEM carrier can offer higher spatial resolution? What are the general principles or why? If you look at the electron source, the electron energy used, in the TEM usually you deal with 100 kilovolts acceleration till to 1,000, right? In the SEM you have 5 to 50. So electron energy in TEM is much higher than SEM. So when you increase the kinetic energy of electrons, you reduce the wavelength of electrons. Right? Acceleration at a voltage is larger, the wavelength is smaller. So in principle, you offer the better resolution. But also, in the TM, you are measuring a very thinner sample. If they're too thick, all the electrons will be scattered, right? You cannot penetrate through the samples. You cannot do the transmission. So very often you are measuring very thin samples. When you measure graphene, it's a single layer can measure a few nanometers thick, right? So the interaction volume, the electron beam volume, interaction volume in the TM is much smaller as compared to the SEM. SEM, your electrons penetrate into the very large area of your sample, very deep, because the sample is very thick. So these are the two common reasons why TM can offer a higher resolution. And scanning transmission electroscopy, you see that this is another more advanced sort of mode of the TM. You add scanning that becomes STEM, STM. What's the difference? It's a conventional TM. Conventional TM, you have parallel electron beam. You have this additional focus lens. You create very small electron probing beams. Okay? You confine them into very tiny spots, very tiny. The probe can be focused to 0.15 to 5 nanometer. Now you can scan electron beam on the surface, or you can move your sample. Typically, I think you scan your electron beam by changing the magnetic field to bend the electron beam light. So in this case, your incoming beam is much smaller, and also the interaction volume of your beam, your sample, is further reduced, right? So that's going to increase the resolution. You can resolve individual atoms much nicer. So there's will be two different modes: bright fields, dark fields. STEM. What's the difference? Bright field, in short, called BF, and dark field, typically you use annual dark field detector. That is this mode. So from this drawing, you already can tell the difference. The difference is that you see, using the dark field, you are collecting the electrons off from this transmission axis line. In the bright field, you detect the electrons that's close to the center of the transmission line, right? So, but in the dark field, we are collecting this off-angle transmitted electrons. This intensity of these diffracted electrons depend on the nuclear charge of your individual site. That basically is the electrons diffraction, scattering. Right? So if your nuclear is heavier, your Z is much bigger, you sort of can bend more of the electron beams. The angle is maybe off. So this bending angle is also related to this, the Z, the nuclear charge on element. Very sensitive. So that's why you can use to identify the position of these atoms, like inside, for example, this one image is the graphene, one image is the ball nitride. They have the very similar structure. In the graphene, all the carbon side are the other side are the carbon. In the ball nitride, you have nitrogen, you have boron, right? So there are two STEM images. From this, can you tell which image is acquired over the ball nitride, which one is over the graphene? Assume that in the monolayer. So if you make the link, the B is the graphene or B is the ball nitride. Can you tell some difference? I think there's some difference. You can see the contrast, right? in the B, all these individual sites, the intensity is the same. It runs similar here. How about this 6 point? A is the bond nitride of graphene. So this one is taking on the bond nitride of graphene. Bond nitride of graphene. Okay. Depend on the nuclear charge Z, right? The bright contrast means the Z is larger for this ADF modes. So A should be bond nitride, right? Because you have this, you have the side difference. One is bright, another is dark. One side corresponding to nitrogen, another side corresponds to boron. They have different atomic number, Z, right? The nitrogen should produce a brighter contrast in this ADF stand mode, right? While in this, if you do all the carbon, you see that the contrast of each side, they are very similar, right? And no difference in the Z. Okay? I'm not sure that's the.
My name is Demike Paptoglu, and I am a staff scientist at Superstem Laboratory in Aylesbury. The Superstem Lab is administered by 5 different UK universities: University of Leeds, Liverpool, Manchester.